All right, 7.3 slope field. A slope field is a graphical representation of a set of slopes obtained from a differential equation. Remember that a differential equation involves a derivative. The derivative represents the slopes for a function. In lesson 5.7, you learned to solve differential equations by separating the variables. Actually, that was in 7.1 we learned that. Separating the variables. Even if you cannot separate and integrate, you will still use a differential equation to plot the slope. So let me redo this because this is actually 7.1. We learned about differential. Okay, so find the slopes given by the differential equation dy over dx equals negative x over y. So here we're finding the slopes. Where do we find slopes? We find slopes in the derivative, right? Well, this is a derivative. So to find that slope at that point, all we need to do is plug in. So I get negative 3 over 2. At negative 1, 3, plug in, I get 1/3. At negative 2, negative 1, with this differential equation, at this point, the slope would be 2 over negative 1, which is negative 2. Here we get 2, so that would be negative 2 over negative 2, which is the value of 1. Next question. Why can't you find the slopes when y is 0? Well, in this case, with this differential equation, we cannot find the slopes when y is 0 because can't divide by 0. And that's it. It's just undefined. Okay, so slope fields. So what's happening here is that we are given a field, and then what they decided to do is plot some of the slopes with it, right? According to this negative x over y. So you will see, remember at 2, negative 2, we got the slope of 1. So if I go to 2, negative 2, I would want the slope of 1. So I'm going to draw or estimate what that would look like. And what it wants you to do is it wants you to start plotting for the rest of these, okay? So if you see it plugged in negative 2 at negative 1, it was negative 2. So that's already plugged in. Negative 1, 3, that's already plugged. So let's see if I can do the rest of these. At 0, we have no slopes, remember, because we can't divide by 0. Let's do this one. This one is at 2, negative 1. So at 2, negative 1, we would get negative 2 over negative 1, which is 2. So again, if this is 1, that means we're going up here. What about at 3, negative 1? Well, that would be negative 3 over negative 1, which is the positive 3. So a little bit more straighter. Okay, that would be 1/2, so a little bit more. So see how that starts happening. And then, of course, you can start kind of imagining what these are going to look like. And, of course, at the x value, right, where y is the number and x is 0, we would have the slope of 0. So we get these slopes. Slopes of 0 are horizontal. So one of the questions that could be an open-ended question is to fill all of these out. Let's see, at negative 1, 1, it's 1. Okay. So guys, what's happening here with this shape? What do you think? So let's look what happens with the rest of these. Let's see if we can get us somewhere with it. So in example 2, you made what's known as a slope field. So filling this out is a slope field. And yes, this could be an open-ended question when you fill that out. Start at the point 0, 1 and follow the flow of the slopes to sketch the solution of the curve containing 0, 1. So the only thing it goes through is 0, 1 that you know of. What you do when you graph it is that you make your graph parallel to the other slopes. So at 0, 1, we're right here. And so if I were to then start following and be parallel to the other slopes there, see how I'm parallel right there? And I continue. But what happens as we get to the x-axis here? We don't have any slopes. So what happens is we have open holes. Okay? Your solution curve must represent a function. Remember, function passes the vertical line test, whose domain is the largest possible open interval containing the given point. Sketch a solution curve passing through -1, 1. So -1, 1 is right here. So I know I'm going to go through those. And I come down, right? Now there's an open spot here since there's no slope. For the rest of it, I'm going to be parallel with those other slopes. And then I hit the x-axis where there is no point. What type of graph does this actually look like? Well, this is producing a semicircle. I don't know why, yes, circle. There we go. No, the most common student error in sketching a particular solution to a differential equation is to extend the graph too far. In other words, the biggest mistake students will make, right, is that you continue and all of a sudden it's not a function. So this is a huge thing. It needs to be a function. And if you do not have a slope, it is an open circle, right? It's a hole. So just be careful. All right, now we're going to actually solve this differential. We looked at the slope field and what it could possibly be. So we're looking at semicircles. Well, let's see what happens if we algebraically solve for this, right? Get your y's on one side. So we get we have y dy equals -x dx. I'm going to take our integral of this. So what we end up getting is y squared over 2 equals -x squared over 2 plus c. I'm going to draw my arrow so whoever's looking at my work in the future can follow it. Now I'm going to get y by itself because as you can see, we're solving for y. So I'm going to multiply both sides by 2. So I get y squared equals -x squared. Now we don't have to say plus 2c because of course it's still a constant. And now how do you get rid of a square? You take the square root. How many answers do you get? You get 2. Now we separate these because we have one is the positive -x squared plus c, and one is a negative square root -x squared plus c. Okay, now this is our general equation, but what we're going to find now is a particular equation. We're actually going to find the function, the equation for this semicircle, right, that goes through the coordinates 1, 0. Oh, I forgot to finish the other one too. Sorry, guys. What I mean by finishing the other one is that it wanted you to do another one that goes through 0, -3. And you will see that when I follow those slopes, it's an upside down semicircle. That helps us with what's happening here. So go back to what I was saying. Sorry to be confusing. This was our general equation. Now we're going to find a particular equation for the one that goes through 0, 1. What I want to point out is since our y value is positive, I know that I must be using the y equals the square root of negative x squared plus c, not the negative one, because y is positive. Now I'm going to plug in my x and y value to solve for that c. So 1 equals the square root of 0 plus c. So of course this means that c equals 1. Now because it wants the particular solution, I need to make sure that I write that function of y equals the square root of negative x squared plus 1, and I am done. Here we're going to find the particular solution, again using the general, but then we want it to go through 0, negative 3. I want to point out right here that y is negative. So that means I'm going to use y equals negative square root of negative x squared plus c. Plug in my coordinate of 0, negative 3. So I get negative 3 equals negative square root of negative x squared. Or nope, that's 0, right? 0 plus c. That means c must be the value of 9. Again, I want to make sure it's a particular solution, so I want that particular function. So negative square root of negative x squared plus 9. And that is the particular solution, the function that would make this semicircle down here going through the point 0, 3. All right, so what does the question look like if it were an FRQ? How are we going to do this? Well, here we have for the differential equation, y prime equals 1 over y, draw the slope field and the dot coordinates. So remember, that's about looking at each coordinate here and drawing that slope to it. Now, and 0, 0, wait a second, can y ever be 0? No, it cannot be 0. So that means there are open spots all here. It does not hit this. Okay, so let's look at when, let's say x is 1, y is 1. Well, y is 1, so 1 over 1 is 1. So I'm going to do that slope. Well, because there's no x value in our equation, that means as long as y is 1, all of these slopes is 1. When y is 2, all the slopes are 1/2. I'm going to try to angle that a little bit different. At y is 3, we have the slope of 1/3. Okay, same thing. As y is negative 1, we get the slope of negative 1. So make sure you're going in the correct direction. Y is negative 2, we get negative 1/2. That's where it gets tricky, guys. You can't draw straight. More flatter for the negative 1/3. All right. Now we're going to graph solutions to the point at negative 2, negative 1. Negative 2, negative 1 is right here. Now, as you can see, I'm going to follow my slopes and be perpendicular. Okay. Now, if I continue up here, what happens at that x-axis again? There are no slopes, so it's open. That makes sense too, because if I started following these guys, do we have a function? No, we don't. So I know it stops. How about 2, 2? Okay, 2, 2. I know it's going to follow here, and I'm going to follow here. Very good. Okay, see, I'm parallel to the other slopes. Now we're going to solve. So I'm going to change this to dy over dx so I can separate those variables. I end up getting y dy equals dx. Take your integral. Get y squared over 2 equals x plus 1. Multiply, right? Multiplied by 2, we get y squared equals, why did I say 1? This should be c, guys. 2x plus c. Take the square root. We get y equals plus or minus square root of 2x plus c. So again, this is the general equation. But now we are actually going to find the exact function that goes through each of these points. So here, let's point out again, the y is negative. So I am going to use y equals negative square root of 2x plus c for the coordinate -2, -1. So now I'm going to plug in. I get -1 equals negative square root of -4 plus c. So that means that c equals 5. So the function that goes through the point -2, -1 is y equals negative square root of 2x plus 5. Let's do 2, 2. Y is positive, so I'm going to use y equals the positive square root of 2x plus c. I'm going to plug in, so 2 equals square root of 4 plus c. Well, that means c equals 0. So for this particular equation, we get the square root of 2x. Yay. Okay, some multiple choice that we might run into. I want you to pay attention to the difference between 6 and 7. Okay, the options we have here are, this is y prime, which means these are the slopes at every point. So y prime, I want you to think of slope at each point. Okay, we're down here in example 7. This is actually the function. Okay, so what can I do with this? Well, here's what I would do. These are all slopes. So I might say to myself, what is one coordinate pair and slope that I can tell is definitely a certain slope? If you look at 0, 0, so I'm going to look at the point 0, 0. I look at that slope and I see the slope of 1. Do you guys see the slope of 1? All right. So in each of these answers, what I'm going to do, or each of these choices, I'm going to plug in 0 for x, 0 for y, and see which one comes out with 1. Here, I would get y prime equals 0. So that's not it. Y prime equals 0. That's not it. Y prime equals 0 minus 0. That's not it. Because again, remember, I'm looking for the slope of 1. Y prime equals 1 plus 0. That looks good, but so does this one. Okay, so right now we're down to D and E. So how can I figure out which one's which? Well, let's try another point. I see that at 1, 0, we have this slope of 1 also. So let me try that. Y prime equals 1 plus, well, what is the y value here? It's 0, so that one worked. But if you look at this one now, we would get y prime equals 1 plus, well, x squared, that would be 1 squared, which is 1. Wait, 1 plus 1 is not 0. So the only answer I can get is D. So I had to go through 2 types of slope to be able to find this answer. Number 7, remember, we're dealing with the function here, right? So what we need to see is when I draw out this function, so let's sketch. Let's say I go through 0, 2. If I look at the shape of this function. So which of these functions is going to have that shape? So that's exactly where I start, okay? So if you look, e to the x looks like this. All right, so that's not the answer. E to the negative x. Well, remember, negative to the x means that I'm reflecting over the y-axis. So if you look, that flips this. So could B be the answer? Yep, that's nice. A negative up front makes it flip downward. So that would look like that. Well, that graphs don't look like that, so it's not C. All right, D. ln, well, I'm going to graph E first because ln of x looks like this. So it's definitely not E, right? Because that doesn't look like that graph. But if we flip this, this looks okay, right? So B and D right now are our only choices. So how can we make this work? Well, let's look at this. Let's go back to our slopes, right? If I look at this slope at 0, 0, we have the slope of -1. But be careful here, because does our function shows us slope? No, we have to take the derivative. Well, for D here, the derivative is -1 over x. Okay, and that's the derivative for D. What's the derivative for B? Y prime equals -e to the negative x. Okay, so let's plug in 0, 0 and see which one comes up with -1. Well, let's start here. -1 over 0 is undefined, not -1. So that's not the answer. Of course, we're left with B, but I want to prove it to you. So y prime equals -e to the -0. Well, -0. E to the 0 is 1. So what do you know? That gives us -1. B is our answer. Again, I had to prove my final answer with 2 ideas from it. Use lessons 7.3 and 7.1. Using lessons 7.3 and 7.1, you should be able to show graphically a particular solution of a differential equation and confirm it by solving. And that is why slope fields are still an option on the FRQ part, meaning this whole idea, guys.